Morning, Tom. How you doing? Do you have a mic or no? If not, you could just type good morning. All right. There's a chat here. You don't have audio. I mean, you don't have a mic, just type and type in the chat. Hello, everybody. Christian, Catalina, great. Tom. All right, so a little slow to get started here today. I have a very full agenda, but I actually think I'll wait a couple of minutes to get started. But first thing I should do probably is ask if you guys were able to do those questions I sent a little bit late. Were you guys able to solve those problems? Anybody have issues with the problems, or you have questions on those? You think so? You got so? Okay, good, good. You can talk if you want, or if you don't want to, that's fine. You can just type. But if you wanna talk, that's cool. I will, let's see, I will pin my video that way. Okay, so you guys can see this on YouTube. Nobody's on YouTube right now, so just us on Zoom. And anybody have problems with the questions, problems with the problems that I gave you? Any issues? Oh, you can't hear anything. Okay, can you guys hear me? Check your sound. Are you guys hearing me? Anybody hearing me?
Yeah, I can hear you.
I can hear you too.
Okay, Tom, check your audio. Maybe it's muted, or what should I do? Check your audio. You can't hear. Check your volume.
Can you hear me?
Who's that? Yeah, I can hear you guys. Who's that?
Okay, this is Christian.
Hey, Christian.
I was able to do those problems and I submitted them. I have no idea if they're right or not, but
okay, all right.
I mean, I got like 12 kilograms for like a boatload of energy, so I wasn't even sure how that made sense.
Okay, just did. It's on high and makes a doorbell sound. Okay, so there's actually, Tom, if you go back, like quit this session, you can actually check your audio when you first, there's actually a browser volume control too sometimes. I don't know why that would be the case. I don't know. But there's a way when you first sign on to say check audio before you join. Or actually there's even if you didn't click the button join with sound or something. Oh, okay, sorry, he can't hear me. Can you hear me? No, you can't hear me, you said. That's right, thank you. Lonnie is typing what I just said, okay. All righty. Okay. If not, Tom, try to go to the YouTube stream and see if you can hear on that. Okay. If not, go to the YouTube stream and see if you can hear that. It's a little out of sync. All right, so Catalina, Johnny, how'd you do on the problems? Were you able to do those problems that I sent out? And yeah, okay, all right. So why don't we check our answers? Should we check that? Should we just do that and see if we got the same answer or not?
Yeah. Yep.
Okay, that would be a way to see. So who wants to? Actually, there's a funny thing we can do. I don't know if you guys have played with this before, but there's actually, if you click on, you guys have the ability. I turned on your ability to share screen. You can actually share screen to a whiteboard, and you can type, right? You can draw. This is awkward, but I don't have a tablet. I know, Christian, you've got one. I want to get one. I think that's what I need. I'm a little bit delayed here. This is hard. Okay, but you can type pretty nicely, right? Typing is much better. Okay, and then after you're finished, you go and grab a little stamp and put a star next to your thing, because that's kind of fun, right? This is important stuff here, right? Astrophysics, the stars, okay? So, all right, I'm trying to be funny. It's not working. Okay, so Tom quit, and now he is, well, we'll see where he is. Anyways, so let's take a look at the problems, and let's see if we can figure out what happened. Okay. Oh, no, Tom is here. Okay, there's Tom. All right. Tom, are you hearing anything yet? Tommy, can you hear me? Can you hear it? Okay. So let's take a look at the problems, and then we'll figure out, you know, what's going on. Okay, so what did I do? I called them practice problems from April 10 lecture. I actually think that I probably need to do it a different way for participation, but anyways, I'm a little bit behind in the grading. You guys might know that. So let's take a look, and I will catch up eventually here soon, because I have to. And here is the problems, right? So the first problem: imagine an electron moving at a constant speed. So why did I have to give you a constant speed? Anybody?
For general relativity to work, they got to be in the same inertial reference frame.
Right. For special relativity to work, you have to be in an inertial reference frame, right? So special relativity only applies to inertial reference frames, and so we'll understand that that's really useful locally, but I think we haven't kind of gotten to the point where we're talking about the expanding universe very much, and there's some real fun issues to talk about, but actually we see things accelerating, and if they're accelerating, it's no longer it's possible to use special relativity. You have to use general relativity to solve the problems. Okay, and they're going to be a little bit tougher. Anyway, so I have this problem: compute the kinetic energy, both using the standard formula, you know, the non-relativistic formula, and then the relativistic formula. Okay, so is it a big difference or a small difference? What's the difference? Okay, so I'm gonna write down the numbers, right? I have a speed of 0.99999 c, and then the mass is 9.10938356 times 10 to the minus 31st kilograms, and I have c, of course, is 2.99792458 times 10 to the 8th meters per second. Okay, so let's go ahead and try to solve the problem. So I'm gonna do the problem right here. Okay, so what is the non-relativistic formula? Ke equals 1/2 mv squared, right? And so I would just put in, 1/2 the mass. Can I just do it? Okay. I'm a little lazy here this morning. Okay, 3, 8. How many significant figures do I want? 1, 2, 3, 4, 5 significant figures when I'm finished. So if I'm writing down a whole bunch of figures, it turns out I'm wasting my time. I do want to keep 6 significant figures, but any more is just a waste of my time. Do you guys understand why? It's not going to affect the answer. I'm going to go ahead and I'll just write them down anyways because I have them. Actually, in general, you might as well use them if you've got them. They do provide a very small difference. And then I've got times 0.99999 squared times 2.9979245 times 10 to the 8th meters per second squared. Okay, so I haven't done the calculation, but you guys can go ahead and somebody want to report? Did you guys? Can you go ahead just work it with me, or look at your answer that you have? And you guys did it this way. So you're going to report 5 significant figures. So 0.5 times 9.10938,356 E31 negative times 0.9 squared times 2.99792458 E8 squared equals. Okay. So I got to 5 significant figures at 4.0935. That's, I got the same answer. Great. 4.0935 times 10 to the negative 14th. And that would be joules. Okay, great. Okay, so we have consistency. So what's the difference, right? The relativistic formula is Ke equals, and we need to use this today. So I really want you to be able to think about it. Gamma minus 1 mc squared. Okay, and so there's a couple of things that I could have done. Well, whatever, that's what we got. Okay, there it is. And so I need to calculate gamma. Gamma is 1 over the square root of 1 minus v squared over c squared. And so for this one, I get a gamma of, anybody tell me their gamma? Why don't you give me a gamma? You should have gotten a gamma. Okay, and okay, 223.6. Okay, I might keep one more significant figure, 223.61, just 5 significant figures. Actually, if I want to round to 5, I might even keep 1 extra, to be honest. Okay, just to tell you that this is what I would do as a professional. I would keep 1 extra significant figure so that I can round it down to 5 when I'm finished. Okay, so that's gamma minus 1. Well, gamma minus 1 is going to be just what? Gamma minus 1 is going to be 222.607. Now I want you to notice something. This, if you use the standard formula, this was nearly C, right? This was C right here. So instead of 0.5, just so you understand, instead of a 0.5, I'm changing it to 222.6. So I know that the energy is going to be 445 times as much energy as I have up here. So what happens is that when you move relativistic speeds, this formula becomes really bad at expressing the kinetic energy, right? So I'm going to go ahead and do the work though. I'm going to go ahead and put it in. Okay, times 9.10938 356 E31 negative times 2.9979 2458 E8 squared. Somebody want to tell me what you got? Thank you. Okay, and I got a little bit different answer because I actually kept more than this even. So the answer that I'm getting is with the whole value of gamma that I got. So even better than this. I got 1.8225 times 10 to the minus 11. So it's just a small difference, but you can see the difference that you're getting is because you rounded the value of gamma off, okay? So it's just a small difference. We agreed to 3 significant figures, but if you wanted to know more, you would need to keep more significant figures during the calculation, okay? All right, so we got that first question, great. Okay, now how about the second question? So what's the error? It's huge. Basically, you were not computing the kinetic energy at all, right? You were getting a tiny little fraction of the real kinetic energy when you're moving this fast, okay? Okay, the nuclear fusion of the sun is naturally converting hydrogen into helium. 4 hydrogen nuclei are used to make 1 helium nuclei. There is slightly less mass in the helium than the original hydrogen, and it is this mass converting into other forms of energy that powers the sun. Okay, so estimate the electrical energy in the United States in 1 year. Okay, so this one is really this is known as a Fermi question, and I thought Tom would like this. But anyways, before you start, you need to come up with a number. So actually, I don't know what it is, but why don't you guys give me a number? Could somebody type a number for the energy, U.S. energy, electric? I think I did electric, right? Did I do electric energy? Electrical energy, just to make it, you know, a little less.
I got 3.09544 times 10 to the 11th kilowatt hours.
Okay, what? One more time. 2.09.
No, 3.09544. 3
9
instead
nine.
of 2. Instead of 2 at the front, it's a 3.
Oh, 3. Okay.
Right.
3.095.
44.
Okay. Times 10 to the
11th.
11th.
And that's from EIA.gov.
One more time. Sorry, what were the units on that?
Kilowatt hours.
Kilowatt hours. Okay. KWH. Okay.
Right.
What's that number? Quad, is that joules? Is Tom's number joules? Okay, and I'm not sure where'd the -1 come from? What's that? Tom, I'm not sure what -1 means. Okay, I'm not. Okay, all right. So anyways, we're having technical difficulties. Oh, Tom, what is 223.607? Okay, so okay, BTU. Okay, well, oh, quadrillion BTUs. Thank you. Okay, so we need we need to have a unit that we agree with. Thank you. Okay. So let's go ahead and let's take Christian's number just for a second. Question number 1 in the kinetic energy. Okay, so the -1, I'm not sure what the -1 is. Is there a -1? Okay, we'll come back to that later. Thank you. All right, so let's go ahead and take a look at kilowatt hours. What is that? So kilowatt. What's that?
Nothing. It's hard to talk with the Zoom. It cuts out and everything. So I'll just type everything.
Oh, wait, you're cutting out or am I cutting out?
No, when 2 people try to talk, it's hard to communicate on Zoom. Period. So
okay,
I think
why don't we do
try
this?
to type.
Hold on. No, I actually want to hear you, please. It's much more fun. if I, what we'll do is we're gonna mute, how do I mute everybody except for the person talking? So we'll just talk once at a time. Actually, how about this? If you guys wouldn't mind, well, okay. Sorry, Christian, can you go ahead and talk and say what you wanted to say? All right, so so Tom gave us a different answer. He put 1.06 times 10 to the 18th. So what I want to do though is let's talk about anybody who might have written down kilowatt hours. That's a valid way to talk about energy, and it's actually the way you get billed for electricity in the US and other places as well. But what is it exactly, right? Kilo, we know, kilowatt, right? That's fine. But then times an hour, which is really, you know, a lot of seconds, right? A whole bunch of seconds. It's 3,600 seconds. How does this work out to be in energy? Well, the watt right here is a joule per second, right? So when you take a kilowatt, which is 1,000 watts, it's going to be 1,000 joules per second. Blah, blah, blah. So what does it work out to be? A kilowatt hour is going to be 1,000 joules per second times 3,600 seconds. And so you end up getting 3.6 times 10 to the 6th joules. Okay, so a kilowatt hour is 3.6 million joules, and that's fine. We just have to then, you know, go back to this and say, you know, is it reasonable? So if you use 3.6 times 10 to the 6 joules for every kilowatt hour, did somebody already do this calculation? Is that the 1.06 for Christian? Okay, so pretty close, right? So using Christian's number right here, we get 1.114 times 10 to the 18th joules, okay? So whoever wrote 1.06, those are kind of in agreement. So can we get a consensus? Does that seem like a reasonable, let's just use it, right? It doesn't, so as long as you're using a number that seems, you know, reasonable to you, we're gonna write down the energy. So 1.114 times 10 to the 18th. And it doesn't matter if you get the exact same number. Oh, so that's actually really close though, right? So Tom's number converting from quadrillions of BTUs is actually remarkably close. And I would consider these numbers, you know, just to be fine. This answer is meant to be an order of magnitude kind of idea. It doesn't have to be perfect. So now what we want to do is use this formula, E equals mc squared, to calculate the amount of matter that would need to be converted into energy to produce this. And the crazy part is, yes, you must have realized how crazy this is. Because C is so enormous, this becomes a very tiny amount of mass. The mass would be E divided by C squared. So Lonnie, your number is kind of big. It's about, it seems pretty large. Again, where did you, oh, you converted from BTUs, 10 to the 20th. I would consider that to be not the same order of magnitude. So we want to look at sources and-
I use the same source as Christian, because he said he also used EIA.
Oh.
I might have done consumption as well as how much was made. Like I might have just used a different total number. Okay.
It's a pretty significant difference though. It's 100 times as much energy, right?
Yeah.
It's 2 orders of magnitude. So actually it's really, yeah, they're really different. We would want to try to figure that out.
I used not only the household, but the industrial, transportation, all of that. So because the question was a little vague on what to use rather than per person or household, it was, I don't remember what the question asked.
Yeah, just
anyway,
as an just estimate it. And actually it's okay. As long as you know what, even Lonnie, it doesn't really matter all that much. It's meant to be that if we had a number here and we wanted to get, I asked you to try to figure out a number for yourself. And if I give you an exam, I'm going to tell you that number, right? But I just for fun to try to see, I had the same as Lonnie. We have total energy consumption, not just electrical. Okay, so actually, Lonnie, that may be that your number ends up becoming the total energy use of the US, which is fine, which is great. That was the later question I asked, right? And then I asked you, even if somebody wanted a challenge, to try to think about the global energy consumption, and that would be an interesting question as well. But one of the ideas, and actually I do want you to think about this and maybe even get excited, is that if we can produce nuclear fusion on Earth, then this is the amount of matter that would need to be converted into energy. It's not exactly right, by the way, because we have an efficiency issue, but it gives us a ballpark, an order of magnitude for how much matter needs to be converted into energy. And so we'll put that number in, 1.114 times 10 to the 18th joules divided by, you know, actually, wow, I don't have enough significant figures. So I'm going to use a smaller number of significant figures per C. Okay, so I'll use 4, which is what I have here, 2.998 times 10 to the 8 meters per second squared. Okay, that's enough because I have 4 significant. I could use 1 more maybe, but that's good enough. Okay, so what do you get? And you get a crazy small amount of mass, right? Which is kind of amazing. And so this is the exciting part, that that's 18th, sorry, 18th. Can somebody check that calculation so that when I get an answer, you can compare it with me? Okay, I got 12.39 kilos. Okay, and somebody said they got 14. That's fine. Okay, it's the right amount, right? We're talking about 10 kilograms of matter converted into energy would supply the entire energy needs of the United States. So just for a moment, imagine, can you hold 10 kilograms in your hands? Can you actually hold that up? Okay, so 450 kilograms. I'm not sure why we're getting such a different answer, but how did I do that wrong? Did I do it wrong? Anybody else get a number like mine? Can I get some confirmation? I think Christian, you said you got 14, right?
I got the same number, 12.
I got exactly the same number.
Which one?
12.39. 399.
Oh yeah, because we use your numbers, right? Of course. Okay, so I'm going to go ahead. Okay, so it's so Tom, which number were you using, Tom? Were you using your value? I think if you look at the orders of magnitude, we have 10 to the 18th, and we have 3 times 10 to the 8th. If you do that, it's going to be about 9 times 10 to the 16th, which is about 10 to the 17th order of magnitude. You can see from the order of magnitude, it should be about 10. Yeah. Okay. So look for the mistake that you made, but we're talking about 10 kilos. That's 22 pounds. Can you hold 22 pounds in your hand? Right? It's just kind of hard to imagine that little mass has that much energy within it. And so matter is a pretty potent form of energy. The problem is, how do you get it out? And so I didn't really tell you the whole story. In fact, it's only a small fraction of the matter that is being converted into energy in the sun. In fact, for every, I think you guys, some of you may know this already, for every 500 million tons. Now, I don't know if it's metric tons or not, but 500 million tons of hydrogen, the number that I've remembered is you get 495 million tons of helium, right? Each second, right? This is the sun. So in the core of the sun, you're converting hydrogen into helium. Every second, 5 million tons of hydrogen mass is somehow disappeared, right? And therefore, it seems like a really huge amount of mass in terms of, in terms of human sizes, of course, but in terms of the sun, it's insignificant. It's a very tiny fraction of the mass. But this is actually what percentage? Well, about 5 million would be 1%. 1%. Wow, that's actually quite big. That's huge. That's huge. But anyways, 5 million out of 500 million is about 1% of the mass is converted, right? So in fact, we lied a little bit, right? In order to get a 10 kilo mass to be changed into energy, we would need to use like 100 times as much, 1,000 kilos. Well, you can't hold that anymore, but we're talking about the amount of mass that goes into a single car, right? And that would power the United States. So if you were able to do this process on Earth, the amount of mass required to make up a single car would be about, would be enough to power the entire United States electrical needs. Okay, so this is a pretty potent form of energy, and that was kind of what the problem was about. All right, third problem. Are we doing the right thing? Is this fun, useful? I know we have to do this, but I have other things I want to do, but let's go ahead and keep going. Okay, did anybody go ahead and do the global thing? The global version? Anybody? No? Okay. All right, so a rocket traveling at a speed of 0.8 c fires a probe in the same direction at 0.9 c. How fast would the probe be moving relative to the Earth? Okay, so this is kind of, so it's a pretty simple problem, actually, pretty straightforward. Number 3, you've got a rocket moving at 0.8 c, and then fires another thing, a probe. I don't know what that means, but maybe, I don't know what even that means. All right, but anyways, 0.9 c, 0.900 c, and the question is, compared to the Earth, what do we see, right? What is the speed relative to the Earth? Okay, so you were supposed to just apply the equation that we talked about in class. So what is the equation for relativistic velocity addition? So I kind of forgot. Anybody remember? Actually, is it on your equation sheet? Anybody know? I think it is, right? I'm pretty sure I put it on there. Let's see, relativistic velocity addition. There it is. Okay. So here is the equation, right? The U, as seen in the stationary frame, is the speed of the frame that's moving, the moving frame, plus the speed as seen in the moving frame, divided by 1 plus v u prime over c squared. Okay, there's our equation. It's on your equation sheet, actually. Okay, all right. You got 44% error for the first problem, 3 orders of magnitude. Right, that's how far off it is, right? For the kinetic energy, is that what you're talking about? Okay, great. Okay, so let's go ahead and apply this formula. And so the frame is moving with a speed, so relative to the Earth, it's moving with a speed of 0.8 c, right? And then the speed of the object within that frame is 0.9 c. And then we have 1 plus, and we have 0.8 c times 0.9 c over c squared, okay? So does anyone see why this has to be is this right? Oh, why does this work? Huh, does it work?
Is the bottom gamma? or like, but not square rooted?
It's kind of like gamma, but anyways, let's just see something. I don't know, why is this not working? Is it working? 1.7 C over what's this number? Did I do this wrong? All right, this doesn't look right to me. Oh, I know what, no. Oh, of course, no, that's not right. What's wrong? Oh, the bottom is 1.72, of course. No, that's not right. 0.9, it is? Oh, yeah. Okay, yeah. Okay, so of course, 0.8 times 0.9 is 1.72. Okay, so the number on the bottom is always going to be bigger than the number on the top. You could kind of prove that. And so you get, you get 0.988 C. Okay, great. Okay, sorry about that. Okay, I just got a little bit glitchy. I actually wanted to see, I'm not going to do it, but if you were trying to prove this, right? Assuming that you're talking about the Earth and some reference frame moving away. So the frame of reference of the Earth is stationary, that's S. And then the moving reference frame is S prime, right? And then within that moving reference frame, we measure speed U prime. Okay, so suppose that the velocity v of the reference frame that's moving is a times c, right? Whatever a is. And u prime is b times c, whatever b is, right? Then what does it look like, right? If I rewrite this equation. So a and b are a number that's between 0 and 1, right? They're numbers between 0 and 1, okay? So why is it that I know that this is always going to work out to be something that is less than the speed of light, right? So I have a plus b times c divided by 1 plus ab, right? A times b. Is there a way to prove that? Anybody want to prove it? How do you prove that? Is that true? There must be a way to prove it. So the question is, can you prove that a plus b over 1 plus ab is always less than 1? Can you prove that? Anybody know how you might do that? Actually, I didn't. I just took them out. Sorry. There's a c divided by c squared. They cancel out. Okay. Everybody see that? Okay. So is there a way to prove that? How would you do that? Why does it have to be less than 1? Anyways, okay, I leave that. I'm just kind of curious. That's a very mathematical question, right? So is there a way to prove that if a and b are numbers between 0 and 1, that this fraction has to be less than 1? So what do you have to prove? That the top thing has to be greater than the bottom thing. A plus b is greater than, less than 1 plus ab. Can I prove that? How do I prove that? A plus b is less than, well, I would multiply both, I'd multiply this by a over a. I get a squared plus ab. Oh, that doesn't work. Nah, that's dumb. All right, I don't know what to do. Anyways, okay, never mind. It's what you get. You forgot to divide by c. 4 cases: 0, 0, 0, 1, 1, 0, 1, 1. Yeah. Just do the 4 cases and show that it works every time. Okay, so Tom is advocating just using the boundaries. So 0, 0, 0, 1, 1, 0, 1, 1. You can show that if you put those in, you always get a number less than 1. Okay, I'm getting off tangent. I want to cover some new material. So let's finish this. If you go to the last question is, oh, not the last question, sorry, question number 4 What is the de Broglie wavelength for a proton moving at 0.1 C, proton moving at 0.100 C, a proton moving at 0.900 C, and then I have, so number 4, and then I have a human moving with a speed of 53 meters per second. That's in a skydive, okay? So it was a comment, don't divide by 0. Okay, yeah, you never divide by 0 because it's 1 plus AB, so you never divide by 0. Okay, but anyways, let's just go ahead and, what's the de Broglie wavelength? The de Broglie wavelength is h, Planck's constant, divided by p, right? That's the de Broglie wavelength. So you need to figure out the momentum. Okay, so now here's a question. Do I need to use relativistic momentum in these two situations? Is it necessary or not? Well, you know what? When in doubt, what you should do is probably just use it. When in doubt, just use it, right? So use the relativistic momentum, which is going to be gamma mv, right? Gamma mv. So it may not be much different, but we just use it anyways. So this is relativistic. Do we need it for the human? Definitely not, right? Then we just use P equals mv. So for both of these, you needed a mass. So you need to look up the mass of the electron. Sorry, the proton. Anybody have the mass of the proton for me? The mass of the proton mass. Wikipedia will help me. Proton mass, anybody? All right, proton mass, 1.67, 1.6726. That's good enough. Times 10 to the minus 27 kilograms. Okay. All right. So you guys got a number like that. Yes. Okay. 1.67. Actually, you're right. So that would have been 1673. I would have maybe kept one extra significant figure. Okay. So let's go ahead and compute for the first case, right? 0.1 C. What is the momentum, right? So I need my gamma, right? So let me do my gamma. 1 over the square root of 1 minus 0.1 squared, which is going to be 1 over the square root of 0.99. Okay, so this is why I probably didn't need to use it, right? What's the square root of 0.99? 0.995, right? 0.995. Okay, so 1 over that. So the answer is so 1.005. It's a tiny little thing, right? Times mass 1.673, 10 to the minus 27 times 0.1 times C, 2.998, 10 to the 8. Okay, and so I get, can you guys check on that for me? The mass, sorry, the momentum. Okay, I get 5.041, 10 to the negative 20th kilogram meter per second, right? That's the momentum. And then H, what is H? 6.626, 10 to the minus 34 joule times seconds. So what's lambda? Lambda is 6.626, 10 to the minus 34, divided by 5.041, 10 to the minus 20th. Okay, and okay, let's try that. Okay, times 6.626 e negative 34. Okay, so I get 1.31, and I think I'm going to stop now, right? That's 3 significant figures times 10 to the minus 14 meters. Okay, so did anybody else get that number? Any confirmation here? Okay, so for the second one, you got the same number. Okay. For the second one, gamma is going to be 1 over the square root of 1 minus 0.9 squared, which is 1 over the square root of 0.19, which is significantly bigger, right? So we got 0.19 square root, 1 over that. So I got P is equal to 2.294. That's my P. I'm sorry, my gamma times the mass, 1.673, 10 to the minus 27, and times 0.9 times 2.998, 10 to the 8th. Okay, we didn't look at the units. Do you guys understand the units? Should we try? Do we understand that? So a joule is a Newton times a meter, which is a kilogram meter per second squared times a meter. And so you divide by the kilograms are going to cancel. That's a good question. I will tell you, Tom, actually, that's a really interesting question. One of the meters cancels. Why don't both of the meters? Oh, times a second, I forgot, times a second. Times a second. All right, this times a second. So that cancels one of the seconds and the other second cancels. Okay, and you're left with meters. Okay. Okay, so Tom's question, why have you never heard of a proton microscope? Because you need to have a source of protons. And it turns out a source of electrons is much easier than a source of protons. Now, you can actually make a proton microscope. You could do that. And what would be the benefit? What would be the benefit of using a proton microscope? Anybody have an idea why you might do that? Okay, and the answer is because you can get a greater momentum, perhaps, right? If you can get a greater momentum, then the wavelength becomes smaller. You get better resolution, right? You can have potential, but it's a pretty difficult problem. So to make a coherent beam of protons is pretty difficult. It's much easier to work with electrons. It's much easier to accelerate. In fact, that's one of the things that we want to talk about today. How do you make them? How do you make these, prepare these in a way that you would be useful? Okay, so now let me get the momentum. And let's see, so times 1.673, 27 times 0.9 times 2.998 E8. Okay, did you guys get a number like 1.036 times 10 to the negative 18th? Kilogram, sorry, kilogram. What am I doing wrong? Clearly is that wrong? No, that's right. That's good. Kilogram meter per second. And then the lambda would be H divided by P. So invert times 6.626. And I get 6.40 times 10 to the minus 16th meters. Okay. Okay, great. Okay, so we have confirmation. So you got a much smaller wavelength with a higher velocity proton. Okay, the faster you go, the smaller the wavelength becomes. How about a human? Okay, so we need a human, and you got to use a human mass. What's the mass of a human? I don't know, 80 kilos, right? 80, 100 kilos. I don't know, 80 to 100, something like that. 80 kilos. Let me put 80 kilos. I'm actually more than that now that I think about it. 80, 70, it doesn't matter. Yeah, this is all just reasonable. 90, that'd be fine. I'm going to use 80. Okay, so 80 kilos, and then I had my speed. And the speed that I gave you is supposed to be the speed of a skydiver in free fall. That's their terminal velocity speed. So what's the momentum? It's mass times velocity. We don't need to use relativistic momentum. You'll get the same answer, by the way, if you use relativistic momentum. And then what's the wavelength, right? So what is the wavelength of a human being that's moving? And so we get 6.626, 10 to the minus 34. joule times seconds divided by this thing, 80 kilos and 53 meters per second. Okay, I didn't put 0.0. So anyways, we're going to get a pretty tiny number, as you can see. So 6.626 E34 negative divided by 80 divided by 53. Okay, and so I get, this is tiny, 1.56, which is about 1.6 times 10 to the negative 37 meters. Okay, which is, yes, less less than the Planck length. Okay, so this is not perceptible and will never be, right? Well, maybe it's not even possible. Maybe it's actually shorter than the wavelength that is even possible for anything. But anyways, this is the reason why it doesn't make sense to describe the wavelength of a person, right? Our mass is too big. So even we just can't achieve a high enough momentum to make a wavelength that is big enough. No, that's the wrong way to say it. Our momentum, maybe I'm thinking of it wrong, right? When we go very small speeds, doesn't our momentum become very small? So actually, maybe I'm wrong. We just have to slow the person down, right? So maybe if I had used a walking person, you know, like 0.8 meters per second or something, I don't know, then I would get something small. But anyways, you could already, we have a problem, right? Unless this is incredibly small, a crawling person. Okay, 0.1 meters, and even then it doesn't work, right? A stopped person. Okay, now we have a problem, right? P equals 0 with the wavelength, infinity. Okay, that's not right. That can't be right. So let me just ignore the problems that we just elucidated and then move on to the next question. What is the momentum of a UV photon with a wavelength of 200 nanometers? Okay, so the last question. If you're given the wavelength, number 5, just ignore this problem. Okay, the wavelength is 200 nanometers, right, which is 200 times 10 to the minus 9 meters, which is 2 times 10 to the minus 7 meters. Okay, that's the wavelength. What is the momentum? So the momentum, we learned, is kind of the inversion of the de Broglie wavelength, is h over lambda, right? H over lambda. So this is h 6.626 10 to the minus 34 joules times seconds divided by 2 times 10 to the minus 7 meters. So it's not very large, but it's something, right? And so a single photon doesn't have a lot of momentum, but if you stop and analyze what light is, it's a whole stream of photons, right? Lots and lots and lots and lots of photons. In fact, that's kind of an interesting question that maybe we can try to answer. How many photons would there be? And so, yeah, you got an answer? Yep, sounds good. Okay, he just did it in his head, 3.31 times 10 to the negative 27. Okay, and then did you figure this out? Kilogram, yeah, kilogram meters per second, if you work it out, right? So you get a Newton times a meter, and don't forget the second, right? Which is a kilogram meter per second squared times a meter times a second. One of the seconds cancel, the meters are squared. The meter cancels here. One of the meters cancels here. One of the seconds cancels here. And so you get kilogram meter per second. Okay. All right. So that was your homework, and you guys are supposed to upload that so that you get credit. And now let's talk about something new. Okay. So we are on to something new. That took a little while. Okay. Hopefully that was useful. And I guess I'll put problems like that on the final. Okay. So what I want to talk to you guys about is the electric field today, the electric field. And what is it all about, right? The electric field. And so before I tell you about the electric field, I need to talk about electric charge. Have I talked about electric charge? I don't think I have. Electric charge, right? Electric charge. Where does electric charge come from, right? And well, that's an interesting question. Where does it come from? It turns out that the basic elements of electric charge come from the charges that we're used to, right? Electric charge, when we think about it, the basic elements of charge are going to be coming from the atoms that make up what we're used to playing around with. Make up humans, and everything that we touch is made of atoms usually. So it's got protons and neutrons and electrons, right? But where is the electric charge coming from, right? Well, so protons have a charge of +1 E, right? Neutrons have a charge of 0 E, and electrons are -1 E, right? And if I were in the lecture with you guys, I would want to tell you this really fun story about this E here. And the E, anybody know what that E is? E is called the elementary charge. And it doesn't mean simple, it means the smallest amount of charge that can be isolated during an experiment, right? It's the building block of charge, right? There's nothing smaller that we can isolate in a laboratory. And the discovery of this is actually a really cool story. It's such a fun story. I love it. It's just so cool. It's called Millikan's oil drop experiment. And what he did is he created this really neat apparatus. And his apparatus, actually in the middle of this apparatus, I want to tell you the punchline first. He had to make these tiny little oil drops, and actually they were like a mist. So if you remember, have you ever seen the old-fashioned perfume bottles? They have a little a nozzle, right? Some kind of a plunger that you push down, right? And then there's a mist that's created. There's a mist, like my sound effect. There's a perfume, right? There's a little tube that sucks up the liquid, and then this is a squeezable bulb, right? A squeezable. Yes, I agree. Tom says it's quantized and not continuous, and infinitely divisible. Squeezable bulb. It is very interesting, right? Charge comes in these basic units, right? And so Millikan did this experiment that actually first identified it. So what you get when you squeeze this bulb is you get a little spray and lots of little tiny droplets, fine little spray, right? And if you watch them, they very slowly fall under the influence of gravity, right? But pretty slowly because they're so tiny. And I don't think we'll talk about too much, but that's a really interesting problem. How quickly do they fall? And it has to do with this idea of drag. So you can't even see my little droplets, but there's little droplets, right? These tiny little droplets. And actually, if you study this, it would be kind of neat. There's a force of gravity that's pulling down on the little droplet, a single droplet. But what happens is they reach a terminal velocity, and there's a force of drag that's just as big as the force of gravity. And so they drift just slowly down at a constant rate. And the finer the mist is, the slower it will drift down. The larger the particles, the faster they will drift down. Anyways, he did that. That's kind of a central part of his experiment. But what he did is he put them in a very special place, right? He managed to spray them between these plates, right? And these plates were kind of something that we talked about last week. they were connected to a battery. And the positive terminal was on top, and the negative terminal was on the bottom, right? And he sprayed this mist of particles in between the plates, and he saw something remarkable. He could make them hover, right? There were some that were hovering. Actually, in order to see this, by the way, he used a kind of a microscope / telescope. He actually was watching with a telescope, and he had a way to measure how fast they moved, right? He actually had a special grid that was built in to his device to allow him to watch the particles and measure their speed. Yeah, it's a kind of telescope microscope. Yeah, I guess it's microscope, sure. I think in my description that I read, it was called a telescope, but it's very close to the particle. So yeah, that's actually microscope. But anyways, he looked at them and watched them very carefully. Some of them were hovering. And why would they be hovering? Well, because something was canceling out the force of gravity. And then spontaneously, he watched them. They would start to either go up or go down. And that was really remarkable. And what meant he was able to calculate what was happening was a little tiny bit of charge was either hopping on or hopping off. And the little tiny bit of charge he was able to show is called the elementary charge. So either 1 or 2 or 3 were hopping on, or 1 or 2 or 3, a very small number, were hopping off. So the elementary charge again, right? What is this? The elementary charge. So he was able to calculate this number, and you want to know this number. It's 1.602 times 10 to the minus 19th. And the unit is called the coulomb. And we'll talk about why today. The coulomb, abbreviated to C. Okay, that's the number though, the elementary charge. So it's a pretty neat experiment. And what it comes down to is that this is the smallest amount of charge that we seem to be able to measure. And he gave this charge to these particles that we now know are the electrons, okay? So we gave the electrons these negative charge. So what I'd like to do is show you a very silly little demonstration, a very silly little animation to help you see something important. Everybody see the sweater and the balloon, right? See, I turned off the charges. Don't look at that. Actually, why not? Let's look at the charges right here. If you notice in this particular picture, all of the positives and negatives are balanced, right? Every positive has a negative. And that's matter, right? Matter is neutral. The number of protons is balanced by the number of electrons. But what happens is you can take a balloon and you can rub it on a sweater, and something interesting happens. It sticks, right? It sticks to the sweater. So I'm turning off the charges on purpose, right? But you can understand something that's going on, right? What happened is the process of rubbing the balloon on the sweater caused charges to be transferred from one object to another. And we call this static electricity. And everybody has experience with this. It's part of our life, right? Static electricity is a significant force in the world, right? And we have experience dealing with it. And sometimes it's fun and sometimes it's annoying. But anyways, it exists. And what it is a charge transfer, okay? So now, did we rub the wall? And the answer is no. But what happens if I put the balloon close to the wall? It sticks to the wall as well. What the heck is going on, right? See, I kind of get this, but I'm not sure I get this. So let's look at the charges and take a look at what happened, right? So what happened when I rubbed the balloon on the sweater? What did it grab? It grabbed the negative electrons. And this is actually what the balloon material does to a sweater. And so by taking away negative charges, the sweater becomes positive. By gaining the electrons, the balloon becomes negative, and opposites attract. Does that make sense to everybody? Opposites attract, okay? But why would the balloon be attracted to the wall? What's going on there? And so you have to watch very carefully, right? Look at, I love the simulation to try to give you this idea, right? What does it do, right? The negative charges in the balloon don't move around very freely. They just get stuck in some place, right? But they push on the electrons that are in the wall, and the electrons in the wall are going to move away a little distance away because they're repelled. But the positive centers don't move, right? And this is actually a physical fact. The materials that we deal with on a daily basis, the atoms, have these larger, not larger, but larger, the mass is the nucleus, and they are relatively fixed. They don't move around. It's the electrons that are able to move around. So when you look at a solid material like a piece of wall, the reason the balloon sticks to it is because it has repelled enough electrons to provide a positive area left behind. And this is called polarization. So the word is polarization, right? So you want to write that word down. Okay, the word polarization. Polarization. Actually, induced charge is another term. Induced charge, sorry, it's a temporary charge that exists because of the electric field of a nearby charged object. That's the word. Sorry, not polarization. Let's use induced charge. Polarization is also going to be there, but let me get back to that. So the induced charge is a temporary charge that exists because of the electric field of a nearby charged object. Okay. All right. So, oops, why did I do that? Let me go back to my picture again. So the polarized, sorry, it's not polarized. The balloon is inducing this charge in the wall. It's a temporary charge. When I take away the balloon, it goes back to normal. Okay, so this is a temporary thing. It's very different from this right here. So let me get back to the word polarized in a few minutes. Okay, I will talk about polarized because it's kind of interesting. Okay, so anyways, yeah, all right, that's it. Okay, so what? Okay, so what happens in the world is we get positive charges. How do you get a positive charge? A positive charge, charged object, is an object that has lost electrons, some number of electrons. Okay, a negatively charged object because the protons are fixed, right? The protons are going to be stuck. So that's what the animation is meant to show you, that the positive charges can't move around. A negatively charged object normally in everyday situations gained electrons, okay? So certainly in the little oil drop experiment, what does it mean that the particle wanted to drift upward? What would the charge of the particle want to be in order to drift up? Well, it's attracted to the positive side, the positive plate, right? This is the positive plate, and this is the negative plate. So what would be the charge? And the answer is, what's attracted to a positive is a negative charge, right? A negative charge. But if you see it drifting down, it either lost its charge, is zero, or it has a net positive charge. And the way that this was happening is the electrons were jumping on or jumping off of the oil droplets, okay? So he had actually, he didn't understand completely how it worked, but he was able to figure out the amount of the electrons charge in this way. So we're going to be learning a way to figure out why, when things are positive and when things are negative. There is actually a really wonderful method for figuring that out. And yeah, anyways, we'll figure this out in a minute. Okay, so you have a negative, sorry, I meant to tell you one more thing. So anytime you have a charged object, we're going to talk about the charge of it, the charge, right? What is that? And it's going to be the letter Q. And the idea is that how do you make it? Well, you either gained or you lost some number of elementary charges, some number of electrons. So it's always going to be some whole number, right? So it could be 0, a positive or a negative whole number of elementary charges, right? So N is a whole number. And do I want to say whole number or natural number? What do I want to say? A whole number? Does that include the negatives? I don't remember. Anyways, I want to say negative, 3, ... Negative 3, negative 2, negative 1, 0, 1, 2, 3. What are those called? Somebody help me out here. What is that called? Is that a whole number? Whole numbers just include 0, right? I don't remember. I'm not a mathematician. I should know more. What is a whole number? Just include 0, right? How do you get the negatives? The integers? Yeah, whole number. I just mean integers, right? That's an integer. Positive and negative integers. Okay, that's the word I wanted to use. Integers. Integers. Integer. But including 0, right? So integer. All right. So yeah. So back to the story. What's going on, right? So we have this very simple idea. If I have something that is a positive Q, and I have over here something with a negative Q, what happens? They attract each other. They feel a force of attraction, right? There's a force, an electric force of attraction. And if you have 2 positive charges, positive Q and positive Q, they don't feel attracted, they feel repelled. Okay, 0 is an integer. Thanks, Tom. I'm not feeling confident. Okay, here we go. There we go. Electric force. Okay. So attraction or repulsion, those are the 2 possibilities for the electric force. Why does it work, right? What's going on? Actually, before we, actually, I'm going to go ahead and tell you. Never mind. I'm going to go ahead and just tell you right now. I'm not deriving it. I'm just going to tell you that the strength of the force between them depends on the sizes of the charges and the distance between them, right? We'll call it R, the distance between them from center to center. And so this is called, it's known as the Coulomb force, or the electric force, right? Okay. And what is the equation? It's equal to some constant, the Coulomb constant, times Q1 times Q2. So basically this was Q1 and this is Q2, right? Q1 and Q2, or this one is Q1, this one's Q2, something like that, divided by R squared. So when you look at this equation, one thing that you want to notice is it looks a lot like what equation? Which equation have we talked about before that looks just like this? And I know you guys are talking about it. What is it? Come on, what is it? Gravitational, right? It looks a lot like the gravitational force, Newton's gravitational force. But it's not, right? It's something different. It has charge, right? But it's the product of the charges divided by R squared, okay? So this is, I'll be very careful here. This is the magnitude of the force. Okay, the magnitude of the force. Yeah, it looks like Newton's gravitational force. But it's not mass, right? And so the way that the gravitational force worked is a single mass has a gravitational field nearby, right? So there's a kind of a field. And so we have a gravitational field near a mass. And the further away you get, the weaker the field becomes, right? It goes like 1 over r squared, right? Okay, there was this gravitational field, a region of influence near the mass, right? And so it turns out that we have something similar with electric charges, right? When we have a single electric charge, it exerts an influence on the region of it. And so we created this concept called the electric field. What is the electric field, right? The electric field. And the definition of the electric field is based on the force idea, right? It's the definition is based on the force, right? It has a magnitude and a direction. Let me start up with the magnitude. The magnitude of the electric field is based on, right? It's the force on a small positive test charge divided by the test charge. Okay, that's what it is. That's the definition. So down here, the electric field is the electric force divided by, let's call it Q2, something like that. That's how you find the magnitude. The direction is the direction that a small positive charge would want to move, right? Or the way that it would be affected by the interior charge, by the central charge. Okay, so I actually, instead of drawing lots and lots of pictures, actually, which is cool, which is actually really something you're going to need to do, I do want to show you on PHET. Let me go ahead and get onto here, you guys. There's so many fun little tools here, by the way. PHET right here, simulations. I like the HTML5, but I don't know if they have all of them. So I'm going to go here and I'm going to look at electricity, right? Electrics. And I want to look at charges and fields. And here's the 5, so that's cool. It's HTML5, okay? And so same with this one. So these are the ones that are going to be a little bit easier to operate. They'll work right in your browser. Oh, this is silly. This one is totally silly. This one is so silly. I shouldn't even bother, but this is actually a little fun joke, right? This is John Travolta. And night fever, night fever. Okay, you guys may not even know that, but he scuffs his feet on the door, right? Static electricity, right? And if his hand is further away, it takes more charge building up. Yeah, it's silly. Okay, don't do that. All right, anyways, back to what we want to talk about. Okay, this is a really fun little app. Okay, so you see you can put in positive charges or negative charges. And let's start off with a negative charge, okay? And you'll notice something. This shows you, it shows you arrows, right? And those arrows represent the electric field, right? The electric field. And so what's going on, right? The electric field, remember, is the direction that a small positive test charge is attracted, right? And so you can see this is my small positive test charge. It's getting really strongly attracted when it's close. It's not very strong when it's far away, right? So this is trying to show me the field that's nearby. Okay, there's a field that's nearby. Okay, so in fact, if you have a negative charge, right, you have this charge in the middle that's called, let's call it Q1, and you're nearby, right? You're actually nearby, or a distance r. It turns out that that distance r could be anywhere on a circle then, right? right? You're going to be the same distance away. And kind of like gravity, what direction does it point? Well, if you're anywhere on the edge of this circle, then the electric field is going to point inward, right? The electric field is a vector that points inward. How do you calculate it? Well, you put in a little test charge, Q2, and you calculate the force, right? So E equals K. Oh, I forgot to mention what K is, right? Q1 over R squared. That's the electric field. The electric field is this electric force divided by Q2. Okay, I forgot to tell you about K. So I really need to tell you about K too. But anyways, what do you end up doing? You divide and the Q2 goes away. So it's just going to be K Q1 over R squared. So it's a nice simple formula. What is K? K is called the Coulomb constant. Okay. And there may be a more precise value, but the value that I have in my head, anybody know it, is 8.99 times 10 to the 9th. Okay, that's the number that I remember. 8.99 times 10 to the 9th. And you can figure out the units. It's newtons meter squared per Coulomb squared. You can figure out the units because when you put it into this formula, this is a Coulomb and this is a Coulomb. Coulomb squared is going to cancel. And down in the denominator, you have a meter. Meter squared is going to cancel. You're going to be left with the units of newtons, a force. Okay. So the idea is that for a negatively charged particle, the electric field points inward, right? This is a negative charge, less than 0, negative charge. For a positive charge, right, Q1 is greater than 0. Then when you do the same thing, you go to a distance R, right? This time, the electric field is going to point away from the charge. Okay? So it's going to point away. So the electric field tells you automatically by the direction whether it's a positive or negative charge. And the strength of the electric field is found by this formula right here. So what is a value of charge that you and I might deal with, right? I mean, I realize I told you about the elementary charge, but it turns out that that's a pretty tiny thing and not something that you and I would deal with. If you were dealing with a balloon that you rub on your hair, then it turns out that a typical Q is in the micro Coulomb range. Okay, maybe nano Coulomb, but it turns out this is actually a pretty typical thing. You could probably create this without too much effort. So micro, what does micro mean? 10 to the -6 Coulomb, right? So this thing, a Coulomb, is actually a huge amount of elementary charges. It's really huge. Remember that the elementary charge was 10 to the -19. So we're talking about a huge number of charges in order to create this little amount of charge right here. But let's try this. Let's try, actually, you know what about the simulation? I just realized they have, what do they have? They have nano coulombs. Okay, so maybe I should have said nano too. Okay, what's nano? Nano is 10 to the -9. Okay. So that's what they're using in the experiment. Okay, so why don't we go ahead and go back to the experiment for a second, or the simulation. And I'm going to put in, so I have a -1 nanocoulomb, and I'm going to measure, okay, the electric field. Now, the electric field, it's not working. I don't see the electric field. I don't see the electric field, huh? Yeah, okay. All right, so I have to actually, I don't see electric field. I don't see it. I see another term, which I didn't want to get to yet. So anyways, let me talk about something else for a second. Okay, so if you guys remember, We have this thing called the electric force. I actually think we should calculate. Let's do one. I need to do one. I'm sorry. Q1, let's do is, negative 8 nanocoulombs. Okay, we'll use nanocoulombs. I've got a charge. What is the electric field um, 50 centimeters from the charge? Okay. So I have a sample problem for you that let's try to do, okay? So we have our charge, Q1, negative 8 nanocoulombs, right? What is that? Okay, we'll come back to that. And I'm over here somewhere at a distance, R is 50 centimeters, which is really 0.5 meters, right? I need to use meters for my calculation. So what is the strength? So first of all, what is the direction of the electric field? So if this is my place where I want to generate the electric field, remember that it's a negative charge, so it's going to be towards, right? Whichever way that a positive charge would be influenced. So the electric field is going to point towards it. It's a vector, right? It has a magnitude and a direction. And the strength of it, I'm going to find by this formula that we wrote down, KQ1 over R squared. Okay. So it's a pretty simple calculation, 8.99 times 10 to the 9th newtons times meter squared per coulomb squared. Okay, I'm going to use the size of the charge. I'm not going to use the sign. And so I'm going to put 8 times 10 to the minus 9 coulombs. And I'm going to divide by 0.5 meters squared. Okay. All right, so actually this 10 to the positive 9 cancels with 10 to the minus 9. That's kind of easy. And then I'm gonna, do the math. Okay, so what about the units? Oh, one of the C's cancels, the meter squared cancels, okay. And I'm gonna be left with the Newton per coulomb. Okay, so can you guys verify the answer for me? I'm going to do the calculation. So 8.99 times 8 divided by 0.5 squared or 0.25. Okay, and to 3 significant figures, I got 288. Okay, the units are newtons per coulomb. Okay, that's the units. Okay, the units are newtons per coulomb. Okay, so I've done a calculation. I've shown the direction of the electric field. I've shown the magnitude of the electric field. I'm kind of done, right? I did the problem. But I do want to share with you that this leads to some interesting ideas, right? What happens when you have 2 charges, right? What happens when you have 2 charges, right? So actually, if you know calculus, you can derive this idea for yourself. But imagine I have 2 charges here, Q1, which is like, negative, I don't know, negative 8. We'll say the same thing, right? Nanocoulombs. And over here, let's say I have a charge that's actually here. Now I have a second charge here and make it positive 5 nanocoulombs, right? Something like that. There's my Q2. And the distance is, 0.5 meters away. Okay, so I've got this thing. Now I put a charge there. Basically, I put a charge at that same location where I just asked a second ago, what the force would be. And so there's an interesting idea that if you remember, the electric field was the electric force, the magnitude of the electric force divided by Q2, right? Which was K Q1 Q2 divided by R squared divided by Q2. But if you wanted the force between these two, what would you do, right? And the answer is, well, you just bring the Q2 over here, right? So you want to write this equation down. that if you want to calculate the electric force, you could use this expression, right? And actually, I'm going to put the arrows in because I want to show you that it actually works. I'm going to show you that it actually works. Okay, so, or you could go back to this formula right here. If you know E, then this is the way to go. If you just know the Q's, then this is the way. Then this is the way to go. So I know both the Q's, right? But I just did the calculation. So in fact, I also know the electric field from a second ago, right? I just calculated the electric field, and it was about 288 newtons per coulomb. That was the electric field. And it was pointed in this direction, right? So take a look at this equation right here. This is a vector symbol, and that's a vector symbol. And I want to show you that this in fact works. If it's a positive charge, then what direction will the force be? Well, the same direction as the electric field. But if this is a negative charge, what happens to the direction of the vector? When you put a negative in front of a vector, you flip to the other direction. And so this thing works, right? It actually works. It gives me the correct direction when I put in the charge sign, right? S-I-G-N. If I put it in, I get the correct direction for the force, which is one really neat thing for you to recognize, okay? So you could use this equation, but if you have the electric field, you can use this equation. You should get the same result. Okay, does everybody see that? So which way does a positive charge want to do? It wants to fall towards the negative charge, right? It's attracted. The positive charge is attracted to the negative. Okay, and we can calculate the force, right? We can calculate the force. It's going to be, positive 5 times 10 to the minus 9 coulombs times 288 newtons per coulomb, right? The coulombs cancel. And I actually have the original number in my calculator, so I don't have to round it off, but I'm going to times 5e. I get a pretty small number. I get 1.44 times 10 to the negative 6. Okay, everybody get that number? Okay, so all right, back to the part that I want to share with you. There's a very interesting thing here, right? If I were to if I held this proton or this positively charged particle and I let it go, it's going to be attracted to the negative charge. It's going to start flying towards the negative charge. It's actually going to start moving, right? And so what kind of energy does the particle have if it starts moving, right? If it's a particle that has mass, then it has kinetic energy, right? It's going to start gaining kinetic energy. Well, that's a funny thing. Where does the energy come from? And the answer is, well, from somewhere. Kinetic energy. Where does the kinetic energy come from? Is it created or destroyed? Right? And the answer is no, that's not possible. It comes from a concept called potential energy, right? So there is this thing called electric potential energy. That's a lot of words and letters, so I'm probably never going to write it again. I'll call it EPE, electric potential energy, or PE. I'm just going to call it EPE. I like that. I like it. It's a nice, simple phrase. Okay. And it distinguishes potential energy, gravitational potential energy, right? It's electric potential energy. And the idea is if you take two charges and you put them close together, and then you move them apart, right? Or maybe leave this one alone and move this one away. You have to put in work, right? Physics work. You have to exert a force and move it away from that charge. And the work that you do is actually the electric potential energy. So those of you who know calculus, you can derive the electric potential energy formula for yourself. If you take two charges, here's the definition, right? If you take two charges and they are infinitely far apart, okay, you can't really do that, but it just means very, very far apart, then they have no attraction to each other, right? You can figure that out because the electric force K, Q1, Q2 over infinity squared is basically zero. There's no attraction. What we're also going to say is the electric potential energy is zero at that point. Okay. So the question is, what if this is a positive charge and this is a negative charge and they are attracted for each other? I know they're not because the force is zero, but let's say that they do in fact fall together to be together like this. Then what happens to the electric potential energy? Is it bigger or smaller if they fall together? And the answer is falling lowers your potential energy. That's what it does. Falling, I'm going to write that down. Falling, which means going the way that you would spontaneously go, always lowers potential energy, any kind of electric potential energy or other kinds. Okay, so falling lowers potential energy. So which means you have less than zero, you have negative potential energy. If they're two positive charges, they're never going to go together. In fact, when we push them together, they fall apart. That's the way they fall. They're lowering their potential energy. And when they get to infinity, they're at zero, right? What it means is when they're very close together, they have positive potential energy. So you're not going to be confused if I tell you the electrical potential energy is different depending on the signs of the charges, but it has a beautiful, simple expression. Here it is. It's K, Q1, Q2 divided by R. That's it. And you need to put in the sign. The signs matter, right? Positive, positive, you get positive. Positive, negative, you get negative. Negative, negative, you get positive, right? And you'll see that it works, right? It works beautifully. It's a really beautiful idea. So this is called the electric potential energy. Now, if I was back on Earth, remember this concept on Earth, and we have the gravitational potential energy, PE, was mgh, right? And so if I have, it's basically what causes this is the Earth. It's the attraction that the Earth has for this mass right here. So if you looked at the surface of the Earth, right? I'm exaggerating the mountains right here. The Earth center is way down here, right? The Earth right here. We just talk about the height, right? The height, h. So, you know, you take the mass and you put it up here, or you put it up here, right? It's gaining potential energy the higher you go. So, you know, if you look at a map, a topological map, right? What does it show you? It shows you these elevations, right? It shows you the H everywhere shows you the H. Is that an energy? No, it's just the H, right? It doesn't have energy. And how do you get the energy? Well, you take the mass and you put it somewhere, right? So if you look at a topological map, what does it look like? Well, you'll see something kind of neat. You can see pictures like this. And what is this a picture of? Who can tell me what this is a picture of? What do I have a picture of here? Anybody? Atoms, very good. Okay, but it's a topological map, Kenny, right? You must have seen a topological map. These are constant. Yes, that's right. In fact, it's indefinite. They're constant elevations lines, right? That's what they are, constant elevation lines. It could be a mountain, two mountains, or it could be two valleys. I don't know, right? Unless I give you some more clues, right? Maybe, you know, I give you another, I don't know if there's a clue here. In fact, it could be a mountain and a valley, right? It could be something like that. That's what this could correspond to. And so the circles that I see are the constant elevation lines, right? The constant topology lines. So a topological map shows you these places where you have constant H, right? Constant H. And then if they're more interesting, you can actually, they're contour lines, right? That's what they're called, right? The contour lines will show you when the things are not so simple, right? Kind of interesting too. Okay. So the reason I bring that up is that we have this concept in electrical fields, in electricity, called the voltage. The voltage, right? And when I say voltage, you want to understand what that means. It's actually not voltage. It's really called the electric potential. Not potential energy, the potential. And it is in fact the V, right? It's called capital V, the electric potential. And what it means is it's kind of like, it's like H in the formula mgh. It's very much like this, exactly like this. The problem is that you need the M in order to turn it into a potential energy. And so I'm going to write something down for you right now, that the electrical potential energy is kind of like mgh, except not, right? And what it is, it's going to be Q2 times V, and I'll put a 1 here, and I'll try to explain what this is. So this V1 is the electric potential, that's the name for it, from charge 1, right? So I have this charge Q1, right? Charge Q1. And in order to turn it into an energy, we need to know what that second charge is. And it really is, it's going to depend, right? So I'm going to go ahead and take, this time I'm going to put a positive charge, positive Q1. And I want to show you, actually, I'm going to write down the formula. Here we go. The electric potential formula is K Q1 over R. Well, of course it is, because the potential energy was K Q1 Q2 over R, right? So you could have figured that out, that the electric potential energy divided by Q2 is actually how you can get the potential. But I want to notice something about this. This one uses the sign of Q1, right? This is important. So if you have a positive charge and a positive quantity, what is it going to tell you about the electric potential near a positive charge? Near a positive charge, if we go a certain distance, R, which means there's circles, I have the same potential anywhere on the circle. And the potential is going to be a positive number near a positive charge. And so the name for these constant potential, constant electric potential or constant voltage, is called, just a name, equipotential. And they're just like contour lines, right? Just like contour lines. Okay, so I'm gonna just do one more little quick thing and then we'll take our break, okay? And let's go back to our PHET, because this program is super fun to play with. Actually, I think you really need to play with it, okay? And actually, I'm gonna take away the negative, I'm gonna put in a positive. What do you notice about the electric field? It's pointing away from the positive charge, right? Right, wherever it goes, it's going to do that, right? We don't need the test charge right now. But what I want to do is take out my sensor here, right? This is my sensor. And you see, as I get closer, what happens to the voltage. Right, it's getting really big. Okay, so if I'm some distance, I don't know, whatever it happens to be, I get almost, I get about 20, whatever it is. Okay, it turns out that if I click this, you see I get a ring, and that ring is going to show me my equipotential line, which is a circle. When I go further away, I get a different equipotential line, right? A little bit further equipotential line. So you see I'm creating a kind of contour map, right? And these are positive voltages, positive potentials. What if I have a negative charge over here? Right? If I do it again, you can see I get negative potentials, right? Negative potential. And over here, I get zero. What the? Okay. All right. When you're close to the positive, you get positive. When you're close to the negative, you get negative. But look at this. In the middle, what do you get? And the answer is there was a place where the potential was pretty close to zero. And look what happens to my contour line, right? My contour line no longer wraps around this one or this one, right? That's kind of an interesting thing. Okay, so these are called equipotentials, and you can actually change this by adding more, right? And we change the situation by adding more. See, now I have more positive, less negative. Anyways, it's kind of a fun thing to play around with. You can add more. Every time you do, you get a more complicated situation, right? Ooh, that's kind of fun. And so it's like an interesting kind of funny little thing. But when you're near the negatives, they kind of dominate. When you're near the positive, they dominate. Okay, somebody got a question? Okay, let's go ahead and look back here. Are negative and positive voltages equal amounts of energy? Not energy, Kenny, these are just potentials, right? In order to get a potential energy, you need to multiply by the charge, right? So the last thing is, how do you get the energy, right? So let's say you're near a positive charge. So you have, there's basically a bunch of things, right? So let's make a little grid and then we'll take our break. I want to know about the electric potential energy near a Q1 with a Q2, right? And the possible charges for the possible values are positive Q1 and positive Q2, or we could have a positive Q1 and a negative Q2, or I could have a negative Q1 and a positive Q2, or I could have a negative and a negative. That's it. Those are the four combinations, right? So what happens when you have a positive with a positive? You get a positive electric potential energy. Positive times a positive is a positive. If you have a positive central charge and a negative charge nearby, you get a negative potential energy. But you also get negative potential energy if there's a negative central charge and a positive Q2, right? And then negative is going to give me a positive again. So the answer to your question, Kenny, is what's the energy? It depends, right? What charge is creating the field and the potential, and what charge is feeling that potential? Okay, so we're going to take a break, and then when we come back, we're going to do some fun little calculations and start talking about why this is actually interesting and useful and how to make charges move, right? So I think you will find it very interesting because it will lead to some interesting technology in the future, which I want to talk to you guys about. Okay, so we see you guys in about 12 minutes, 15 minutes, 15 minutes. Okay, 15 minutes. Okay, my time is 11:27. So we'll return at 11:40. 42. Return at 11:42. So I will go ahead and say that, right? Okay. Okay, we'll see you guys in a few minutes.
Hello. Hey, can anyone fill me in on what we did in beginning class today?
Yeah, Kenny. At the start of class, we
Thanks.
went through the homework that he assigned us a couple days ago. He gave us.
Yeah, I did it. Did you get actually can I go over the numbers with you maybe?
Yeah, sure.
Okay. For the first one, I got 1.8 times 10 to the negative 11 joules for an electron moving at 0.99999 C.
Yeah. Did you
You got
also
that?
calculate it classically?
Yeah, did you get that too?
Under classic kinetic energy, I got 4.09 times 10 to the negative 14 joules.
Okay, but what about relativistic?
Yeah, with relativistic, I got the same as you.
Okay, cool. I didn't know that we were supposed to do the classic as well. Whoopsies.
It was so you could explain why
difference.
non-relativistic doesn't work.
I just wrote because the velocity is too fast for the classic.
Yeah, it's since the difference is you're pretty much getting that 1/2 mv squared and replacing
Yeah.
the 1/2 with gamma minus 1. So you go from multiplying by 0.5 to like multiplying by 200 or whatever your gamma ends up being, which is
Yeah, right.
a lot different.
Right. That 1/2 versus 200 is a big difference. Okay, cool. The energy consumption, I'm guessing a lot of people got different answers for. Seems kind of weird. We're supposed to look
Yeah.
up. We're supposed to
Kind of
look up.
depends where you looked it up from or what number you used. For my problem, I didn't really write down the examples we did because I think we used Christians.
Okay.
But I found like the total energy consumption, not just electrical, like total energy,
Yeah.
which was
Global.
not global. I just did the United States.
Okay. Yeah.
And mine was about 1.07 times 10 to the 20th joules. I had to
Okay.
convert it.
I got 10 to the 19th joules, so that's close enough.
Yeah, and then so depending on it, also like I imagine it depends on the year you use too.
I used 2017.
Yeah, I used 2019. So
Okay, that actually makes a lot of sense then. There you go. It would be a little
and
less.
converting it to weight, mine was like 1,000 kilograms.
Yes, so E equals MC squared. You put C squared on the bottom of E.
Pretty simple conversion.
Yeah, and then you get M equals E over C squared. So joules on top and then meters per second on bottom, speed of light on bottom squared. And then I got about, so I guess the mass of hydrogen required to fuel the United States for the year 2017 would have been 163.85 kilograms of hydrogen.
Yeah, that's pretty close to the example they got.
Okay, cool. Well, I'm glad that we got something similar.
It sounds like you definitely did it right. So
number 3. I got 90. We should have the exact same answer for this, I think.
yeah.
Got 98.84%.
I didn't write it as a percentage. I just put 0.988 C.
Yeah, perfect.
Yeah.
Okay, cool. I wrote it as a percent. Same thing. The de Broglie wavelength, whatever. I got for A 1.25 times 10 to the negative 14.
All right, we probably use some different rounding on like the speed of light or the mass of the proton. But mine was I got 1.321 times 10 to the negative 14th.
Okay, well, the most important part is the 10 to the negative 14. So
Yeah, same significant.
yeah, I always got to make like that's the first thing. You got to make sure that's right, and then the other one's probably just slightly different use of numbers or something. I don't know. Did you put gamma in this one? Did you do the
So
wavelength?
that's the thing that I remembered in the class. We actually figured out when you need to start using gamma was around 0.3 C. So I didn't bother until B, where it was at 0.9 C. I definitely used gamma there, but the difference between gamma and not using gamma is pretty negligible since the gamma was 1.005.
Yeah, exactly. It was a very small number, so it's pretty insignificant, right? And then so for the proton moving at 0.9 C, did you use gamma?
Yeah, I sure did. My gamma was 2. Did I put that 2.294?
Okay. I must have did something wrong there. Oh, did I forget to square it? I think I forgot to square 0.9. That's what I did wrong. Because I got like a 316 or 3.16, but I think it's because I forgot to square the 0.9. I'm pretty sure. Let me just check real quick to see. Did you get 10 to the negative 16 though for B?
Yeah.
Okay,
sure
cool. So that's good. So but you didn't get 4.64 because
I got 6.41.
yeah, and that makes sense because I think what I forgot to do is I definitely forgot to when you're writing the gamma equation, you have to do 1 over the square root of 1 minus, and then it's the 0.9 C squared.
Yeah.
So you get 0.9 squared equals 0.81, and then you do 1 minus that. 0.81, 0.19, and then you have 1 divided by the square root of 0.19. And sure enough, you get 2.29. So
Sweet.
Okay, and then the C, the human moving, that one was weird.
That one was funny.
I don't know. I got a really small number though.
Oh, it's so insignificantly small. What'd you get?
Oh, okay, good. Oh, that is right. Okay, I got 1.92 times 10 to the negative 37.
Yeah, man, that's less than a Planck length.
Yeah.
I got 1.71. We probably used a slightly different human weight.
Yeah, I used 65 kilograms.
I had 73. So.
Okay, cool. That's more like my weight anyways. So 5p equals h over, 5 momentum equals Planck's constant over the wavelength.
Yep.
So I guess I got for the momentum, 3.313 times 10 to the negative 27.
Yep, I got the exact same.
Okay,
Kilogram
cool.
Times meters per second.
Yeah, and it's okay, interesting. So momentum is kilograms times meters per second, but then like joules is kilograms times meters squared per second squared.
Joules is like a Newton or joule. It's a joule per second, right? Planck's constant is in joules per second. So
joules times seconds.
Yeah, my bad. Joules times second.
Yeah, Planck's constant is joules times seconds. And since 1 joule is kilograms, meters squared, seconds squared, and you have a second in a meter, you cancel those second in a meter.
Exactly.
And you're left with meter and second, which is pretty cool.
That was the homework. After that, we started talking about electric fields. I don't know what part you hopped in at.
Yeah, no worries. I understand that we're doing electric fields today.
Yeah, they're pretty similar to gravitational fields, which is pretty cool.
That's really cool. Because aren't gravitational fields like huge and electric fields are like tiny?
Oh yeah. But the math looks the same.
That's crazy. That's interesting. Well, thanks,
Yeah.
Lonnie. That's good. I'm glad
Yeah, no
we
problem, Kenny.
we got that settled. I got the same answers for the most part, basically. That one part I messed up, I know why I messed up, which is good. It's able to understand why.
And that's what it's all about.
I know, seriously.
All right, I'm gonna go grab a quick drink.
All right, man.
All right, I'm back. You guys ready to go? You guys ready to hit the road again?
Yes, sir.
Okay.
Yep.
All right. So let's talk a little bit more about this this potential. So yeah, I actually want to try to give you guys an idea. So maybe I don't actually know exactly where all the charges are located, right? So maybe I just want to kind of set up a hypothetical situation, right? I know that there's this voltage right here. Let's say it's positive, 500 volts. Okay. By the way, the volt is the unit of the electric potential, and so this is actually an introduction for some of you. You've never heard of this before. When I wrote down for you the electric field, I told you the units were newtons per coulomb, right? Newtons per coulomb. That was the electric field. But it turns out it's not just newtons per coulomb. There's another unit that you can use. And it comes from a very simple concept. Actually, I'll come back to that in just a few minutes. But let's see, what else can I show you though? I need to show you something else. Okay, well, I'll just show you whatever. We have the electric potential energy was, you take a second charge, Q2, and you put it in this voltage, and now it's a potential energy, right? So it's Q2 times V1, right? And so if I look at the units, we know the units of electrical potential energy are joules, right? And we know the units of charge are coulombs. So what is the unit of a volt, right? What is a volt? What is a volt? So a volt is a coulomb. So the unit of charge times the unit of voltage or potential, sorry, equals the unit of energy, equals a joule. So a coulomb times a volt equals a joule. Does that make sense? So we'll come back, and there is another way to describe electric field, and I'll talk about that in a minute, okay? But I have this story I want to talk to you guys about, okay? So let's say I have this Q2. I haven't told you whether it's positive or negative. So just keep that in mind. And then over here, I have another contour line, another thing right here, which is going to be, I know I'm calling it V1. Can I just, shoot, now I'm getting confused. Shoot. Okay, well, what do I call it? Okay, I don't want to call it anything yet. I want to call it something else, but all right. V1 meant from, but this time I'm not going to know where it's coming from. It's not a single charge anymore. It's a whole collection of charges. So that's actually why I want to talk about it like that. So I have this thing that's representing, a collection of charges and the impact on the environment. And then I have another one over here. So I actually want to call this something though. I want to call this initial. How about that? The initial. And then I want to actually have a final over here, the final. And I'm going to write down a different number. Let's put positive 300 volts, right? And I want to talk about this charge moving between these points, right? And how does it do that, right? What happens when that occurs, right? So one of the really interesting things is that when you're using the energy picture, it doesn't actually give you all of the details. It kind of sweeps past some of the details, but it gets you the right answer, right? So one of the things that's kind of interesting is it turns out it doesn't matter how you get from here to here, right? How does this charge move from here to here? I actually don't know. And if I'm worried about energy, I don't care. It could be direct, or it could be along some other path. It actually doesn't change the problem. It's kind of like, describing when you look at the energy picture, just saying that I get from here to here, it doesn't really matter how I got there. I could, go if these are two different elevations, right? The total change in energy is determined just by these 2 points. So this is initial and this is final. Okay, so how do you get potential energy? Well, potential energy, remember, is Q times V. Q times V. And so the Q that I'm moving around is Q2. And then I'm going to have VI, meaning the initial voltage, which is going to mean that there's an initial potential energy. And the same thing is true for the final, right? The final potential energy is Q2 at that final voltage, okay? But I can see from the numbers that the voltage went down. So what happened to the potential energy? Did it go up or go down? Anybody?
Goes down 200.
It goes down in potential. Does it go down in potential energy?
Oh, it goes up in potential then.
Up in potential? Okay. It's actually a trick question. There's no right answer, or both answers are correct. So anyway, sorry about that. But I was hoping maybe somebody would say that. It depends on the what? It depends on the sign of the charge. Okay. So whether the energy is going up or down depends on the sign of the charge, right? If it's a positive charge, there's one answer. And if there's a negative charge, it's the opposite answer. So let's go ahead and try to understand that. So what I want to think about is the change in the potential energy. What happened to the potential energy? Did it go up or go down, right? And the answer is, well, I got this. And what does change mean? It's always the final minus the initial. So it's Q2 times the final electric potential minus Q2 times the initial electric potential. Well, I could factor out the Q2, and it's just Q2 times delta V. So you should write that down because that's pretty useful. If you want to find the change in potential energy, you take the charge times the change in the voltage. Now I can really describe what happened, right? So in this particular picture that I've used, I know the change in the voltage. It's 300 minus 500. So it's negative 200. Negative 200 volts. It went down 200 volts. So I still need to know what Q2 is. All right, so electric potential energy, sorry. So let's say that it was a positive charge, right? Then what happened to the potential energy? Did it go up or go down? If I had a positive charge times a negative number, what do I get? I get a negative change in potential energy. So I lost potential energy. But if this is a negatively charged particle times a negative change in voltage, then I gained energy, right? So you really have to think about the story and then identified what's happening to the charges. But let's say it's a positive charge. Suppose that Q2, that the charge that I'm moving is a positive, you know, I know I'm going to use a big number, but let's say it's a positive, oh man, I know I said to use nanocoulombs. Let's use nanocoulombs. Let's go ahead, use nanocoulombs. So positive 10 nanocoulombs, okay? So then what happened to my potential energy? I got positive 10 times 10 to the minus 9 coulombs times negative 200 volts, which means I have 10 to the positive negative 8 times 200. I have negative 2 times 10 to the, this is 10 to the second, times 10 to the minus 6 joules, okay? So what happened when I went from that 500 volt line to the 300 volt line is I lost energy. Okay, you know what? This is just so vague and weird. Let me do something easier. Okay, let me talk about something easier. But I actually want to use this concept, but maybe for a real simple problem. Okay. So Actually, this is a problem that I might give you. I might actually give you this on a, in fact, maybe I should give it to you this week. I'm going to take a charged particle and make it a positively charged particle. And Q1 is positive. I'm going to make it a little bit larger this time, 50 microcoulombs, 50.0 microcoulombs, okay? So remember that that's positive 5.0 times 10 to the 50 times 10 to the minus 6, or 5 times 10 to the minus 5 coulombs now. That's a pretty big charge. And I'm not drawing different distances, but I'm going to go ahead and, yeah, I guess I am actually, sorry. There's an R1 and there's an R2. Actually, I want to make this R final, so I'll make it R final. And then there's R initial. And actually, let's make the Q2 be a negative number. So let's see, R initial is, 0.8 meters. That's supposed to be 0.8. This is like 0.4. 0.4. Okay, about half the distance. Okay. So now I need a Q2. Let's go ahead and let Q2 be a negative quantity. And the negative quantity is negative, I don't know, 10 microcoulombs. But this time I'm going to also tell you the mass. Okay. And it's going to be a pretty small mass. Let's say 5 times 10 to the minus third, 10 to the minus 6 kilogram. Okay. So that would be 5. That's actually 5 milligrams, right? It's the same thing. It's a little tiny mass, a little tiny particle. So it's 5 times 10 to the minus 6 kilograms. Everybody understand the problem? So what I want to do is I have actually this particle right here. This one is going to be fixed, right? It's held in place. So it can't move, held in place, sorry. And I'm going to let this thing go. And which way does it fall? Well, it falls this way. So that's why this is the initial radius and this is the final radius. So there's more than one way to solve this. And actually, that's great. In fact, I should probably solve it in multiple ways just to show that I get the same result. But anyways, you can, because I have the charges, you can actually directly compute the change in the electrical potential energy. You can directly compute it, okay? And the way you do it is you take the final minus the initial, right? And you're going to use the equation for the electrical potential energy. I'll write it up here. It's K Q1 Q2 divided by R. Okay, so we can directly compute it. Okay, so so the only thing that's changing is the value of R. That's kind of useful to remember. So we have K Q1 Q2 divided by R final minus K Q1 Q2 over R initial. Does anybody know something mathematically we could do? I mean, why don't you do this, right? Factor out K Q1 Q2. And then we just have 1 over R final minus 1 over R initial. This saves us time in the long run, right? Because we don't have to keep putting these things in multiple times. All right, any questions? You got that? Okay, so what's going to happen? Is this number going to be positive or negative? Which one? Positive or negative? I gave you a problem. A negative charge is near a positive charge and it's falling in. What's going to happen to the potential energy? It's going to go up or go down? I can't hear you all if you all talk at once. Down. Okay, Tom says down. Thank you, Tom. Okay. All right. So the answer is down because it's falling in this direction towards the positive, which is what it wants to do. And whenever you fall, you lose potential energy. So you're going to lose potential energy. It's going to be a negative quantity. Okay. So I'll do the calculation. 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. Okay. Times Q1 positive 50. Sorry, 5.00 times 10 to the minus 5th times negative 1.00 times 10 to the minus 5th. Okay, times, put a bracket here, 1 over 0.4 meters minus 1 over 0.8 meters. Okay. Okay, so let's see. Can you guys do the calculation with me, and then let's get an answer when we're done. Okay, so I'm doing the calculation. I'm going to do the fraction part first. 0.4, 1 over 0.4 minus 1 over 0.8. Okay, I got 1 over 0.8. I got this value right here. So I got 1.25. Okay, and then times 8.99 E9 times 5 E negative 5 times 1 E negative 5. Okay, so I got a number, right? I got a number of 5.62. Okay, it's a nice number, 5.62 joules. Okay, did anybody else get that number? 5.61875.
So that's the energy that this particle has when it's jumping from Q2 to Q1.
You got that? Okay, great. Okay, so now why did I give you, oh, I got a negative, sorry, negative. I forgot the negative. Don't forget the negative. This is important, right? The change in the electric potential energy is negative 5.62 joules. So why is that important? Well, because we lost potential energy. Can anybody tell me what must have happened? As we fell in, what happened? Okay, so we sped up, we gained kinetic energy. There must have been a gain in kinetic energy. How much? Positive 5.62 joule, right? There's no calculation needed. If I lost potential, I gained kinetic. Whatever I lost in potential is what I gained in kinetic. And so if this thing was initially at rest, which I probably should have said, right? I should have said that. Initially at rest, right? Then what's the final question? How fast is it moving, right? How fast is it moving? Okay, so do you think we're going to need to go relativistic at this point? The numbers don't seem too big. What do you think? Probably not, right? Okay. Probably not. Okay. So I have my kinetic energy. It's 5.62 joules. I don't need to use a relativistic formula. It's 1/2 mv squared. Okay. So I want to solve for V with this kinetic energy. It's my V final that I'm trying to get. So multiply by 2 on both sides, divide by m. Okay, and take the square root. So V final equals 2 times the kinetic energy divided by m, take the square root. Okay, there we go. So 2 times 5.62 divided by the mass, 5 times 10 to the 0.00 times 10 to the minus 6 kilos, take the square root. Okay, so you guys want to try to give me an answer for the final speed. And I just erased the last number. Oh, well, okay. There we go, I got it back. Okay, times 2 divided by 5 e negative 6. Take the square root. Whoa, okay. The final speed is 1.50 times 10 to the 3rd meters per second. That thing is booking, right? It's really moving fast. Okay, but not that fast. I mean, it's reasonable, something. 1,500 meters per second. Whoa. And so this would be a little tiny like dust particle or something. Actually 5 milligrams, not insubstantial. But this is a significant speed, right? By falling a little ways, right? It didn't fall very far.
Sean,
Yes.
the mass seems kind of big. I don't know why, but milligrams seems like if it was a particle, it would be like in the micrograms.
Yeah, actually for a dust particle or something, but this is a little like, I don't know what it is. Some kind of maybe a little styrofoam ball. How about that?
Cool. Yeah, just curious.
Okay. So yeah, something. Yeah, you're right. I agree. It is kind of big, but look at the speed already. You know, we're getting a pretty significant speed, 1,500 meters per second. Okay. So that's a really good point, Kenny. Thank you for that. So actually, I want to show you guys another kind of interesting situation and a pretty important scenario for you to understand. And this is back to this thing called the parallel plate capacitor, right? And it turns out something kind of interesting. A parallel plate capacitor has a really special feature, and that is, how do you make it, right? How do you make it get charged up? You connect it to a battery, right? And I showed you guys that the long side of a battery symbol is the negative side, right? That's the negative side, the negative plate, and here's going to be our positive plate once I connect it up, okay? And this battery, actually the real name for a battery is called a potential difference. And this is an important idea, right? If I connect a 1.5 volt battery, that's a AA or a AAA battery, at least nominally, it's supposed to be 1.5 volts, right? What it means is that this end of the battery is 1.5 volts higher than this end. And if you connected that to this pair of plates, something very beautiful happens. You get this really interesting, very, very kind of beautiful electric field. The electric field is nearly vertical. Okay, except for the edges where it kind of curves out a little bit. Curves out a little bit. Okay, you can't see it, but it curves out more the further away you go. Okay, don't worry too much about that. And the direction, well, what direction would a positive charge go if I put it between the plates? It would go down. So the electric field is pointing vertically down. And if we ignore the edge effects, which is what I'm talking about here, if we ignore the edge effects, then it's very uniform. So one of the great things about this, the reason it's so useful, is it creates a very uniform electric field. So you want to know, why do we use parallel plate capacitors so much? Because of this, right? It creates a very uniform electric field. And in fact, right, it's kind of a simple idea, and it's actually a constant electric field. A uniform meaning a constant electric field, right? Between the plates, very uniform electric field. So when you are talking about the potential difference between the two plates, that's delta V, right? That's delta V. Then you can quickly describe actually the change in potential energy too, right? If you take a positively charged particle, positive Q2, then I have to push against the electric field to make it go up, right? Is it going to gain or lose potential energy? Well, it's going to gain potential energy. If I had the positive charge up here, it would fall in this direction. It would lose potential energy. If I had a negatively charged particle here, right, a negative Q, it would fall this way. They fall up, right, and would lose potential energy. But a negative Q2 up here, I'd have to push it in this direction to make it go. So it would gain potential energy. Anyways, it's kind of an interesting idea. So remember that the change in the electric potential energy is just Q delta V. But it turns out you may also remember that the way that you can figure out the potential energy is by the physics work. And the work is the force times the distance. And the force at any point is going to be the Q times the E, right, that I need to exert against the electric field. So the work is actually going to be the Q times the E times the D. So this work is actually also the change in the electric potential energy. If I do work against the field, I gain electric potential energy. If I let the field accelerate me and move me, I lose potential energy, right? So the work that I do against the field is a gain in potential energy. So if you look at these two formulas, they have to give you the same result. Then you end up with something kind of beautiful, that the change in the voltage is the electric field times the distance. So if the distance between the plates, call that D, is D, right? The distance between the plates is D, then the electric field strength between the plates is just the potential difference divided by D. And this is true when you have parallel plate capacitors. So if you hook it up to a battery and you know the voltage of the battery and you know the distance between the plates, you can figure out the strength of the electric field. Okay, so that's a lot. We're doing a lot of stuff very quickly, and I'm sorry about that, but I think it'll be kind of fun for you guys to see that this is in fact how you make little tiny charged particles, electrons or ions, protons. In fact, you can accelerate them. Yes, an ion, right? How do you make? Yes, I know, ion propulsion. Yeah, Kenny, you're gonna love this, right? This is actually where it comes from. How do you create it? You need a potential difference and you need a distance for that potential difference to be applied. And then you get this uniform field in here. So let's go ahead and let's do 1.5 volts, but this time let's put an electron in, okay, or a proton. Well, let's do both, right? Let's do a proton. Where would I put a proton to have it fall? At the top or the bottom of the plate? Top or bottom plate? Where would I want to put a proton to have it fall? Okay, so if you put a proton here, it's not going to go anywhere. It likes the negative plate. So you want to put it right up here, right? So if I have a proton, I put it here. But if I had an electron, I would put it here. And in the process, it would fall, okay? So I want to use a AA battery, and I want to ask the question, depending on the distance, right? Actually, it doesn't matter, it turns out. It doesn't matter what the distance is. The electric field is going to change, but the potential energy won't, right? So how fast would a proton theoretically be moving if it was accelerated by a AA battery? How fast, theoretically, would an electron be moving accelerated by a AA battery? We're talking a AA battery here, okay? This is not super advanced technology. It's something that you and I can put our hands on, right? But it's the question I want to ask, right? I want to use a AA battery, 1.5 volts, to make this happen. Okay, so let's go to work. Okay, so we saw where we want to put the proton. The proton is going to accelerate in this direction down. An electron is going to accelerate up. They're both falling, but they fall in opposite directions in the electric field, right? The electric field is actually exerting a force on them, and then as they move, they lose potential energy and they gain kinetic energy. All right. So should we do some extra work, or let's do some extra work before we do that? Let's go ahead and let's use a and AA battery. And so now I'm telling you that nominally that's 1.5 volts. And a gap of 1 centimeter. That's my distance to create a proton accelerator. Okay, so you understand what I'm saying, right? That I now have a potential difference between the top and the bottom plate. And I'll make the top plate be the positive and the bottom plate. It doesn't matter though, right? It actually doesn't matter at all. And this is 1.5 volts of potential difference. That's the delta V. 1.50, sorry, 3 significant figures. Where will I put the protons to accelerate them? So I'm going to need to put a little hole in the plate, but it doesn't matter. I'm going to inject protons that are moving at a speed of initially about 0. And I'm going to put them in the top plate, right? There's my proton, positive proton. So what are the things that I need to know? I need to know the charge. What's the charge of a proton, right? And it's positive 1.6 times 10 to the minus 19, 1.602, 1.60 is fine, times 10 to the minus 19 coulombs. And what's the mass? 1.67 times 10 to the minus 27 kilograms, okay? So I've got the charge, I got the mass, I got the delta V. What is the change in the electrical potential energy? Okay, so you want to understand something. What happens when the proton falls, right? What happens to the delta V? It's going to be negative 1.5 volts, right? So it's going to be, it's losing the potential because we want to lose potential energy. So we have a positive 1.6 10 to the minus 19th coulombs times a negative 1.5 volts. Okay. And then what is the amount of kinetic energy gained? Well, that's going to be a positive, whatever this number is, right? So actually I can do this. What's 1.5 times 1.6? It's 2.4, right? Times 10 to the minus 19 joules. Okay, so it doesn't seem like much, but in fact, we're going to see that because the mass is so tiny, that's actually a pretty significant amount of kinetic energy. So do I need to use the relativistic formula? I don't know. I don't think so. I don't think so. It doesn't need, AA battery probably isn't enough to worry about. But you know, you can always go back later and say, wait a second, the speed that I get is way too big. If you get a speed above the speed of light, guess what? You screwed up. If your velocity, so by the way, I messed up. Make sure this is a big V. Capital V, right? Capital V for volts. Make sure it's a big V, okay? Because I'm about to find little v. If little v is bigger than C, or it doesn't even have to be a little bit, bigger than C, you made a mistake. Use relativistic KE, okay? But you'll notice that you don't have to, there's no relativistic form of the potential energy, just leave it, that's what it is, okay? So what's happening? I'm gonna lose potential, that's Q delta V, and I'm gonna, if I use the positive version, that's fine, equals 1/2 mv squared, right? I'm going to gain kinetic. So whatever I lose in potential energy, I'm going to make these both positive for this particular situation, right? Then I'm going to get, so I'm going to turn this into the positive version of it. So in fact, it's actually, in this particular case, it was Q negative Q delta V. Sorry about that. I mean, if you want to put in the real delta V. So delta V was, delta V was negative 1.5 volts, right? Okay, it just becomes positive. Okay, so how do I get the V? I'm going to get V squared equals 2 times this energy I mean, we've done this a million times. I'm just going to put it in 2.4. Nope, 2.4. Sorry, times 10 to the minus 19th joules divided by m, 1.67, 10 to the minus 27 kilograms, and then take the square root. Take the square root of that. Okay. All right. So what do we get? What's the speed? So 2 times 2.4 e negative 19. Can you guys check the numbers with me? Divided by 1.67 e 27. Take the square root. Okay. So anybody get a number? Can you give me your number? To 3 significant figures. 1. Anybody?
16953.
Okay, so just 3 significant figures. We'll go 1.70.
1.69. Yeah, 1.70. Thank you.
Okay, times 10 to the 4th.
Yeah.
Okay, so we're pretty far away. We're much less than c. We're fine, right? We didn't need to use relativistic speeds. But if you look, right, that's a pretty big speed. A proton is moving 17,000 meters per second, 17 kilometers per second, when it's accelerated by a AA battery, right? Just so you understand, a proton is moving 17 kilometers per second with a AA battery. Okay. What about, let's repeat it with an electron, right? So what's going to change? What's going to change, right? So this is an important question. What's going to change? This time, the electron has to be accelerated from the bottom plate, right? The electron is going to be accelerated from the bottom plate up. The charge of the electron is negative, but it's going to accelerate up. The delta V is positive. So what happens to the change in the electrical potential energy? It's the same amount. The electron loses the same amount of energy. The only difference is that the mass of the electron is much smaller, 9.11 times 10 to the minus 31. So everything here is the same. We just replace this mass with the electron mass, right? So for the electron, the speed is going to be a much greater quantity, right? Let's try that out. So 2 times 2.4 e negative 19 divided by 9.11 e 31, negative 31. Take the square root, and you'll get a much larger speed. What'd you get? 3 significant figures. 7 point. Yes, a AA battery can make an electron escape from the Earth. Isn't that crazy? You only need 11 kilometers per second to escape from the Earth. What do we get? 7 point, yeah, thank you. 7.26 times 10 to the 5th meters per second. All right, so are we getting close to relativistic yet? Not yet, no. But we're only using a AA battery. My gosh. So a AA battery gets you 100,000 meters per second. Crazy, huh? That's crazy. A AA battery will do that. Okay.
I just looked up the speed of ion propulsion, and so xenon ions go 90,000 meters per second out of the back of a.
Okay, well, Kenny, we're going to learn how to make them go even faster than that, okay? Okay, so you need to know that we have an interesting idea. And actually, in particle physics, it turns out we are accelerating particles all the time. And those particles are actually going to be fundamental particles, or particles that are, have charges that are pretty close to the elementary charge. So it turns out that it's a quick little thing, but either way, in other words, whenever you accelerate a charged particle in a delta V, it's going to lose potential energy, right? It's going to be negative, negative whatever, right? The absolute value of Q times the absolute value of delta V. Okay, it's always going to be that, right? If you're accelerating a particle. And so you want to understand that there's a quick way to refer to this process. And by the way, so then what happens to the kinetic energy? If you lose potential energy, you have a negative accelerating a particle. Then what happens? You gain, right? A positive absolute value of Q, absolute value of delta V, right? It's always going to be a positive quantity. You gain kinetic energy in that process, no matter what, okay? That we ended up often using elementary charges, right? And so this is actually the source of the particle physicist idea, right? If we're using an electron or a proton, it's an elementary charge. And we use a voltage, which is measured in V. And so we get this thing called the electron volt. And so it's the energy gained, it's kinetic energy gained by an elementary charge, an electron or a proton, for every volt that it's accelerated by, every volt of potential difference that it's accelerated by. And it's just the charge of the electron, 1.602, 10 to the minus 19th coulombs, times 1 volt of potential difference. And this works out to be 1.602 times 10 to the minus 19th joules. Okay, so 1 electron volt is this, right? So you guys need to know that, because in particle physics, we don't actually talk about the energy in joules necessarily. We're going to use this, right? We're going to use the electron volt, but it's going to be a significant amount. It's not going to be electron volt. It's going to be mega, giga, or now tera, right? Tera electron volts. So actually, let's not go there yet. I just wanted to make sure. Actually, I forgot to do something. I forgot to do something kind of, I meant to do it right here. When we talk about the voltage right here, they talk about the electric field right here. You see it's the change in it's the potential difference between divided by the D. In this way, you can see something kind of important. The electric field can be measured as newtons per coulombs, but it turns out it's exactly the same, and this is a conversion. It is exactly the same as a volt per meter. They are the same, right? A newton per coulomb is a volt per meter. That's what it is. So we have this mixture of units that might be useful later on in our class that I wanted you to be aware of. I wanted you to see this, and I forgot to put that in, okay? So even though I derived the expression, I forgot to tell you it is a volt per meter or a newton per coulomb. So when would you use this? When would you use this? Well, if you know the voltage and the meters, then this is a convenient unit to use. But if you know the force and the charge, this is a convenient thing, right? Okay, so either one, this is the same thing. And I actually thought of another issue, so let's go ahead and we'll do our final little interesting problem, and then I'll give you guys some fun sample problems to try, where you need to start thinking relativistic. Okay, so in an electron microscope, and I used to use one in the lab, and I was really always struck by something very interesting. There is this knob that you use for magnification. Okay, and it's measured in volts. Okay, and so I want you to see if you can understand what I'm talking about here. If you want to turn up the magnification, you increase the voltage, right? I mean, that is literally what you were doing. You turn a knob and you increase from 150,000 volts, right? Maybe it was 100 kilovolts You turn the knob, right? And it turns up to 300 kilovolts. I think it even went up to 350. I forget the exact, but anyways, whatever. I've got this, I've got these. But you see, I'm going to be using thousands of volts, 100,000 volts. So this electron microscope, this is actually going to be a more complicated problem. I don't have time to solve today completely, but I actually want to do one part with you. I want to use 100,000 volts as my delta V, and I want to accelerate an electron, and I want to know what kind of speed do we have. And actually, as a side question, which I will ask you in homework, what happens to the wavelength, right? And so one of the ideas, a kind of a simple idea is, at least as an order of magnitude, the size of the object that you can see is about, is kind of limited by the wavelength of the material, the wavelength of the illuminating source that you're using, right? So it's not exactly the wavelength, but it's related, right? And so you use a shorter wavelength, you can actually get a higher resolution. Right? You can see smaller features in the you know, on your whatever you're looking at. Okay, so what I want to try to do though is I want to use this as my delta V. This is my delta V, 100,000 volts, and I want to ask, what is the speed of the electron? What is the final speed of the electron? Right? What's my final speed? So it's a pretty simple problem, right? I've got the voltage, I know the charge of the electron, and I know the formula to use, right? For the change in the kinetic energy, it's just Q delta V, right? Everybody good? So let's go ahead and just do it, right? Let's do it. So we got Q delta V, we got 1.602. Actually, we could, you want to just use the formula again? We did the formula, right? You take 2 times the change in potential energy divided by the mass, take the square root, right? So if we just apply this, right, it's 2 times 1.6 times 10 to the minus 19th coulombs times 100 times 10 to the 3rd volts divided by the mass, 9.11 times 10 to the minus 31. Take the square root. Okay, so take the square root of that. Okay, so let's get the answer. And okay, so 2 times 1.6 E19 times 100 E3 divided by 9.11 E negative 31. Take the square root. Okay. Okay, so what'd you get? Anybody? I got a 1. How about that? I got a 1. 1 point. What do you think? 1 point. Is Tom doing it? No. Okay. I mean, he's doing it, but I don't have to see an answer. Anybody have an answer? 1 point what?
Oh, I'm still typing it in.
Okay. Yeah. Okay. So I got an answer, but try to get it yourself. And the answer is no problem. It's 1.86 times 10 to the 8th meters per second. Does that sound good? That be good? Anybody? Is everybody happy with your answer?
Yeah, that sounds good.
Okay. Well, I have a problem with it. Does anybody else have a problem with it? What's the speed of light?
Uh, 3 times 10 to the 8, so it's almost the speed of light.
Well, yeah, it's like, it's over half the speed of light. This is relativistic. So guess what? We did it wrong. right? If I see this kind of a speed, then I know that I did it wrong, right? What's the correct energy, kinetic energy formula to use? Gamma minus 1 mc squared, okay? Now, I do want to show you some a neat little thing, a neat little trick. Super cool. I know, Tom, I'm sorry. What are you going to do? I'm waiting 20 seconds, am I not? No. All right, anyway. The neat thing is that when you go look up, when you go look as a particle physicist, when you actually do this as a particle physicist, you don't do it this way, right? I want to show you how you do it, okay? As a particle physicist, when I go look up the mass of the electron, I get this, right, for the electron. Anybody remember what it was? I wrote it down before. 0.511 MeV over c squared. So when I said the electron is being accelerated by 100 kilovolts, that I actually know automatically that the kinetic energy is 100 kilo electron volts. Do you guys see this? Because it's the electron, elementary charge, being accelerated by a voltage, I actually know the kinetic energy is 100 kilo electron volts. So what is the actual formula you want to use? That the kinetic energy is gamma minus 1 mc squared. And the reason why this is not going to be very hard for a particle physicist is because it's all set up for them, right? You put in 100 keV equals gamma minus 1, and you put in 0.511 MeV over c squared times c squared, they cancel. And you've got EV and you've got EV, right? So what is this? 100 times 10 to the third EV equals gamma minus 1. And this is 0.511 times 10 to the sixth EV. All right, the EVs cancel on both sides. And you have a much easier problem. You can solve for gamma, and then from gamma, you can calculate C. So let's go ahead and finish that, and we'll be done for the day. So let's go ahead and can you find gamma first of all? And then from that, can you find V? Okay. Let's find our gamma. And then using this formula, gamma is 1 over the square root of 1 minus V squared over C squared. How do you invert it, right? Flip it over, the square root of 1 minus V squared over C squared equals 1 over gamma. Square both sides, 1 minus V squared over C squared equals 1 over gamma squared. Flip this over here and this over here. 1 minus 1 over gamma squared equals V squared over C squared. Take the square root of both sides, okay? And that gives you V over C equals the square root of 1 minus 1 over gamma squared. And so this will give you the fraction of the speed of light. Okay, that's what you're looking for. Okay, so find to get gamma first. So 10 to the 5th. 10 to the 6th, okay. Anybody get gamma yet? So this is 10 to the 5th, which makes this, if we get rid of this, 0.511 times 10 to the 1st. That's 5. So we get 1 divided by 5 equals gamma minus 1. Add 1 to both sides. Okay, so I get about 1.20. 1.20. Anybody else get that for gamma?
Can you move the screen down a little bit, Sean, so I can see the algebra you did? Yeah, so you have B over C. And we're just plugging in speed of light. Oh yes, I see.
Okay, so okay, so when I do the calculation of this, I get 1.64 times 10 to the 8th meters per second. Now, if you compare it to the answer we got before, you can see that our previous answer wasn't correct, okay? So this was the answer we got, but actually this tells us we did it wrong, right? As soon as you get a speed that's more than, like we said about 0.3 C, so that's like 10 to the, 10 to the, what's 0.3 C? 1/3 of, it's like 1/3 of, like 10 to the 8th. Anything with 10 to the 8th in here, we're relativistic. And so you can see the corrected version of our speed is given here. Okay, this is the correct version of the speed because we use the relativistic version of the kinetic energy formula. Okay, so I have to give you some problems, but we did cover a lot of ground today, and hopefully you guys are okay. Anyways, you can see, I thought I was going to do more. Huh. The funny thing is we did get something done. We got the potential, electric potential energy. We talked about conservation of energy and how that allows you to figure out speed. And so I guess the next trick is to build something. I actually really want to show you guys something very interesting. And for next week then, did everybody get the same answer? You got that? Anybody else? Okay. So for next week, I want to talk about a couple concepts with you, which is actually, sorry, not cyclotron. The old name was, it's called synchrotron radiation. And it turns out that we see this coming from space. And what is it? And how can it be formed in nature? It's a synchrotron is a device. It's a ring-shaped device on Earth. A synchrotron. Okay, like a big donut ring, right? Kind of like CERN, right? And so what is it? It's a ring-shaped device, and the particles are going to move in a circle, right? And so that's an interesting question. How do they do that? How do you make charged particles move in circles? Anybody know the answer? How do you make charged particles move in circles at a high speed, right? Anybody know the answer? Christian, anybody who's taken physics, you know the answer. Magnetic field, that's right. Magnetic field. And so next week, I want to show you guys this really beautiful idea that you can make synchrotron radiation by the magnetic field. And in fact, if we know the kinds of particles that are circulating and we know the frequency of the radiation, that we can in fact infer the strength of the magnetic field. And so I may be able to get to that next week, but it's kind of an exciting part of astronomy to know that magnetic fields are a really powerful part of astronomy around anything with a significant mass, like a star, a white dwarf, a neutron star, or a black hole, supermassive black hole. There's going to be powerful magnetic fields from the region of that thing, for one reason or another. I don't know if we'll talk about where it's created, but at least we'll talk about how you can identify the strength of the magnetic field. Okay, so that's about all I have for now, and I will post some questions for you. I will do a better job and try to post them today. I will post them today for you. And then you can do those for next time. If you have any questions, please stay and ask right here at the chat. And otherwise, I will see you guys next week.
Thank you.
Thank you very much.
Hey, Sean, what was the speed that we got for that last problem? I had calculated it right as you took it away.
Can you see that?
Oh, yeah. So 1.64 times 10 to the 8th. Okay, cool. That's what I got too.
Is this real time? I'm not sure. Oh, I see Tom saying things. I just put this piece of paper down. That's real time. Is this real time? Are you here in real time or imaginary time? Okay, so I'm going to end this. Okay. No, it's not your submission. I am not done with the grading of the midterms. So I was supposed to be done, and I'm sorry, I am not done. I will work on it. I'm working on it today and this weekend, and I will get it done. Okay. So thank you. I know you want to know. I want you to know too. So I will. I'm sure you're doing great, actually, by the way. You're doing great. You're wonderful. You guys are all wonderful. I'm so appreciative of you. Thank you for being here. Okay. Any other questions? Did you just say real time? Did you just say real time? I did. Real time. We are in real time. I did. Can you hear anything now? Are you hearing me? Real time? Oh. Thank you, Kenny. Real time. How come you can't hear, Tom? Why can't you hear? Oh, you can hear now? What the heck? How come you couldn't hear before? What happened? You mean it just didn't work with everybody else? I'm a little confused. I don't know either. Okay, well, that was frustrating for you. I know you were on the YouTube and it's delayed like 20 seconds. So I'm asking the question and I'm waiting and waiting and waiting and 24 seconds. Okay, wow, okay. Well, yeah, so actually I don't understand either. That's kind of confusing.